My name is Bryce Erickson. I'm a fourth year computer science major.
And my name is Hunter Rednett. I'm also a fourth year computer science major. And for our graphics final project, we chose to dive into 3D graphics optimization and specifically progressive meshes and mesh decimation. Um, the first thing that we did, since this was a relatively complex topic, is we tried to ground ourselves in the research at hand. So the first paper that we looked into was efficient implementation of progressive meshes, which was written by Microsoft Research in '98 and proved to be a great paper that a lot of people built off of in the future. The next paper or assignment that we looked into was a UC Berkeley assignment called geometric modeling. This was also a good grounding spot because we were able to structure our code somewhat similar to what they had recommended here. And then finally, we looked into Professor Shah's view-dependent progressive meshes paper that was published last year. We were super excited to get into this project because we both really enjoy the field of just optimizing things and figuring out how to package something in an optimized way as fast and as efficient as possible. A lot of the papers have really complex ways to do so, but we chose to implement the streamlined approach of mesh decimation. And then since we had some more time, we did the reverse to look into how to rebuild the mesh based on the triangles and faces that you have removed over time. So now my partner Bryce will go into the technical achievement, specifically the algorithm around collapsing the shortest edges.
Yeah, so I'm quickly going to go over the function collapse shortest edge, which is our function to remove one vertice from the object. So what we first do is update all the edge lengths. So we loop through all the edges, calculate the distance between vertex V and vertex U, and update that length in that edge. Next, what we're going to do is we're going to get the shortest edge in the graph or in the object. This makes sure that it has the least amount of impact if we were to remove that edge. Next, to collapse that edge, what we're going to do is move vertex U to the midpoint of the edge and then collapse all of vertex's V's neighbors onto U. So how we do this is loop through all the neighbors of V and make an edge between U and the neighbor of V. So you see that right here, we create a new edge, and then we push it back onto the edges. Next, what we're going to do is update all the faces. So any face that contains the vertex V is now going to be the vertex U. So we basically update that index to vertex U now. We're going to remove all degenerate faces. So this means that any face that has two or more of the same vertexes, we're going to remove that face because it's a degenerate face. This usually happens when we have a face that contains U, V, and some other vertex. And when we update V to U, we now have two U vertexes. So we want to remove that degenerate face. Finally, we want to remove all the edges that contain V because we no longer have vertex V in our object. We're going to remove all the edges that contain it. And finally, we're going to update the normals of the new faces we have. This is because as you're changing the shape of the object, the normals actually change. So what we're going to do to update the normals, we're going to check the adjacent faces, get their normals, and then get an average of all the adjacent faces of the face that's affected. And if you can see here, we have this thing called step. This is so when we reverse the decimation, we actually have all the information we need to revert this operation. So we keep track of the original positions of U and V. We get all the added and removed adjacent vertices, and we get all the changed faces, deleted edges. So that's basically gives us all the information to revert it in this function called reverse collapse, but I'll the README explains that more and I won't go into depth about that, but feel free to check the README to get more information on that. But yeah, that was pretty much it. Thank you for listening.
Awesome. Yeah. So thanks, Bryce, for walking us through that. Now I'm going to show us a demo of our actual implementation. We're going to start out with the bunny. So as you can see, we implemented the bunny to just kind of spin around on its own axis. Right now, you can also note that the title of the project shows that the model percentage is at 100%, meaning 100% of the original faces and vertices are intact. What we can do here is also similar to our projects that we've done throughout class is tab to go into filled mode versus wireframe mode. And we can use the right arrow and left arrow to decimate and revert the image at hand. So as you can see, as I click through here, here's the model with 50% of the amount of original vertices. And you can still see that the bunny has its ears intact, the snout, the feet, and the overall shape is relatively preserved compared to the original. And now I'm just going to hold it down to watch the animation go to 0, which is pretty interesting. And as I said earlier, you can use the right arrow key to rebuild your mesh to the original object. The other really neat thing, which was different from the papers, is that we did implement normal mapping. So you can see that the object actually shows the normals, and it just creates a really nice visual effect when you're going through and watching the algorithm visualize. So now that we saw the bunny work, we're going to jump really quickly and look at the monkey. The monkey has less faces, so it's easier to just read 0 as quickly as possible. And it's also worth noting that you can decimate in both modes, and you can see it happen in reverse. It just gives the user a lot of flexibility to kind of play around with different object models and see the algorithm work in real time. Cool. And now that we kind of demoed our project, we're going to go into some of the future optimizations that we would look into if we had more time, or are going to extend this for our portfolio.
Yeah, so for the future improvements, so or at least our first iteration of the algorithms, we want to make a very streamlined approach that wasn't really complex because these research papers have a lot of complexities to it, and obviously it becomes really hard to debug the more complexities you add into it. So what we did instead is every cycle we update the whole object. So we loop through all the faces, edges, and vertices every single time, which isn't really optimal because the more optimal way of doing it is for each vertex, we store the adjacent faces and edges and only update the relevant faces and edges. So it basically turns the complexity into O of n and compared to O of 1, which is the algorithms the research papers mention. But it became really hard to implement the research paper and then figuring out how to revert that because you're changing a lot of objects while you're doing it. And overall, we thought it would be simpler just for this project just to implement a more streamlined approach. Besides that, we can also add like future improvements include like user defined constraints. So potentially allowing users to define like some edges or faces that they don't want to remove to keep that intact. And then the algorithm will basically skip over those faces to make sure that the user can define areas of the object they want to keep. Besides that, I think this is a pretty successful project overall. And yeah, I think we're pretty happy with how it turned out.
Exactly, and thanks for noting those improvements. But also, as we can see, even at 50%, you can still see majority, if not most, of the structure intact. I think if we were using this, if we look at the bunny, for example, even 25%, you can still easily tell this is a bunny, and at 75%, you really can't even tell a difference between the two. So we were super happy with our approach and the overall results, and we're actually really excited to continue working on this after the class ends. So we just wanted to thank you for the time and look forward to seeing everyone else's projects.